issue. And please allow me introduce my colleague from Munich, Yvonne Wedge. She is the market segment manager of aerospace and defense, and she is responsible for satellite application. Yvonne, please.
Hello to everybody, and thank you, Wendy, for the nice introduction. So I like to start my presentation. And so satellite communication is experiencing a drastic change. The transition from video broadcasting to broadband connectivity services, which you can see on the left-hand side, the era of new space, and visit emerging satellite constellations displayed in the middle, and the integration of non-terrestrial networks into mobile communication networks, displayed with the picture on the right-hand side. In the following, I will explain how active phased array antennas master the challenges of future satellite communication networks. Phased array antennas do not need to be active, yet only the combination of both, namely active and phased array antennas, can meet the challenges of today's communication systems, which require high throughput to enhance the capacity of the satellite and adaptation to rising actual user needs. Active antennas are significantly more complex and expensive as compared to passive solutions, but they offer advantages like increased scanning capabilities and reconfigurability in power allocation, pointing and shaping of the pattern, and this cannot be guaranteed with passive solutions. So to make GEO satellites more cost attractive, the costs are to reduce. And this is achieved by increasing the capacity and the throughput per satellite. Active phased array antennas are key here, since they feature high gain spot beams, beam steering and beam forming, and can thus adapt to changing user demands. Very high throughputs, they even require thousands of beams and beams with a very small diameter. So for high gain, you need a large aperture, hence large reflectors are deployed, or direct rating arrays in the magnitude of reflectors. So with many very high gain spot beams, a large area can be covered. Then frequency use and illumination of the beams in a time dynamic way further increase the capacity per satellite. The latter is also referred to as beam hopping. Maybe you have already heard of it. With regard to beamforming, state-of-the-art is hybrid beamforming, which makes out of the advantages of analog and digital beamforming. A fully digital beamforming, it offers full reconfiguration and, of course, more flexibility, but with the drawback of high power consumption and a considerable complexity, especially if a high number of elements are involved. Simpler solutions are therefore desired, which still satisfy the requirements of the applications. A good solution is a modular antenna array. So this is depicted here on the right-hand side on the slide. And it consists of subarrays, so the antenna array, it's scalable, and this leads to a reduction of the control elements. A single antenna can generate in this way multiple simultaneous beams in the coverage area, and even disturbing grating lobes can be kept outside of the field of view. So satellite constellations, they are composed of smaller satellites, and therefore they call also for compact antennas and beam steering, which is needed to serve different applications, even on multiple orbits. Precise beam pointing is required, and digital or optical beam forming for inter-satellite links. Multiple beams for ground stations are required to track more than one satellite at a time in order to achieve a make-before-break handoff from one satellite to another. and an increased scanning angle is needed to track satellites and also for a smooth data handover. However, with increased scanning angles, disturbing grating lobes appear again. And what I've mentioned again, promising technology here provide subarrays. They have the advantage that they generate multiple beams with a reduced number of elements, and the grating lobes can be steered out of the field of view. User demands demand communication services while they are on the move. And this is a rising trend. So mobility is a rising factor. Therefore, terminals are to integrate on airplanes, buses, trains, and so on. So the terminals and the antennas must be compact and conformal. Artificial materials, metamaterials, liquid crystals are promising here. And moreover, they deliver reconfigurable beam steering much faster than mechanical setups could provide. With user terminals comes the need for cost-efficient terminals, and this is still the bottleneck in mega constellations. The evolution of technology and the technology readiness for high volume production will make them then cost effective. Integrated antennas are also a good solution, and they are ideal to address high frequencies. Additionally, standardization is necessary to make everything compliant with the communication network. So now I come to non-terrestrial networks and mobile communication networks. Here still many hurdles are to overcome. So the path loss is one factor, but this can be countered with high gain spot beams of active phase array antennas combined with efficient power amplifiers. However, the high peak-to-average ratio of OFDM, so orthogonal frequency division multiplexing, which will be used in 5G, this will cause the power amplifiers to operate in the nonlinear region. Solid-state power amplifiers are used to allocate power in a flexible way to beams, and they can also better mitigate the nonlinear behavior. On the other hand, traveling wave tube antennas are more power efficient. Then another factor, latency. So for short latency communication, very high throughput satellites are deployed on LEO, so low Earth orbits. Then the mobility of the satellite and the user, they cause a Doppler shift. But with the knowledge of the ephemeris data and the geolocation of the user, the Doppler shift can be calculated beforehand and then compensated. GNSS receiver functionalities are advantages for user terminals. And again, for mobile users, of course, compact conformal antennas are ideal with a wide angular scan. So this slide sums up the before mentioned requirements of future satellite communication systems. Beamforming architectures with increased capacity in terms of number of the beams, beamforming, and reconfigurability are needed. And active phase array antennas are the driving technology here to achieve all these targets. When we consider active antennas, of course, active antennas are involved, which affect the overall performance of the transponder and the antenna. And the trend is that the antennas become more and more integrated. So if connectors between the passive radiating panel and the active beamforming network, if they do not exist anymore, then an over-the-air test approach is the only viable test approach, and this need to be performed at an earlier stage in the production process. And this affects, of course, the test methods and the test values which characterize the overall system. This slide gives you an overview of the test parameters which are vital for passive antennas and which become of interest for active antennas. For passive antennas, antenna systems, conducted and radiated tests can clearly be separated. So scattering parameters characterize the matching performance of the antenna to the feeding network and the transmission properties. If active elements are involved, test quantities which characterize active components, such as amplifiers and filters, need to be considered now. In satellite applications, the gain-to-noise temperature ratio is an important test parameter, which is comparable to the sensitivity value in mobile communications. This picture makes it obvious that active antennas are part of the satellite transponder, and the correct characterization of an active antenna must include specifications about in-band and out-band performance and the generation of intermodulation products. Very high throughput satellites feature many active beams and thus also a complex beamforming network. Many signal paths are to be verified. Since the room is limited, combined transmit-receive modules can be a good solution. And the task is now to measure precisely a large quantity of TR modules. And this leads, of course, to a long measurement time. So conventionally, the TR modules are characterized with a vector network analyzer in a conducted measurement first, and then the TR modules plus the antenna elements are measured in an anechoic chamber. To reduce the test time here, a multi-port MVNA is the best choice since it provides phase-coherent signal stimulation and phase-coherent reception for up to 24 ports. Further highlights include a high dynamic range, high output power level, and fast measurements due to fast sweep times. When we come to radiation tests in an anechoic chamber, here the vector network analyzer, the ZNA, is the instrument of choice for the following reasons. It comes with 4 ports and up to 4 phase-coherent sources. It has an optional second internal LO source, so a fifth source up to 26 gigahertz. This is available for millimeter wave converter support and for use as a general LO source. The second LO is great for measuring frequency converting devices or measuring on a low frequency for keeping the losses in the path low. At the same time, the other LO is available for internal use. So this also speeds up the measurement time. Then it provides up to 8 truly parallel receivers, which feature all identical RF characteristics. And this is beneficial, especially for antenna measurements where you want to measure several signals in parallel, like the reference signal, horizontal and vertical polarization, or several elements concurrently. For modulated signals, several signal generators can be coupled. Synchronizing multiple signal sources is always a challenge. In addition, time offsets of external components, such as cables, need to be compensated. Roeder and Schwarz signal generators present a compact, easy-to-use solution. The generator's phase coherence option enables LO coupling of multiple instruments by distributing the synthesizer signal of one instrument to the others. The high-end SMW, the signal generator, it shows outstanding RF performance. It provides an extraordinary IQ flatness over its entire bandwidth of 2 gigahertz. due to an automatic internal response compensation. And this is a big advantage over the use of a separate arbitrary baseband generator together with a vector signal generator. Plus, it shows extraordinary suppression of carrier and image sidebands over the entire modulation bandwidth. And together with the FSW, so on the signal analysis side, they are the ideal couple to measure noise power ratio, group delay, gain compression, EVM, phase distortion, so all indicators of satellites components performance. The FSW convinces with its unparalleled low phase noise and best sensitivity on the market. It operates up to 90 gigahertz and exhibits an extremely broad bandwidth of up to 8.3 gigahertz. So high power amplifiers increase the gain of active antennas. And they often operate near saturation, and hence they give rise to nonlinear effects, and that can degrade the performance. So conventionally, continuous wave signal is used for testing, and but in case a CV ramp is used as input signal, gain compression graphs show a line as expected. However, only with modulated signals used as input signal, the gain compression curve looks like a cloud. And this is due to memory effects of the DUT. So only digitally modulated signals reveal whether the DUT distorts the signal significantly. And this becomes especially important with regard to non-terrestrial networks in 5G radio, since OFDM signals will be used. The high peak to average ratio will cause the amplifier to operate in the nonlinear region. And it is thus essential to test with the operating signal. So I have already mentioned the ZNA, the network analyzer. And here comes a summary of its advantages for demanding antenna measurements in the SATCOM field. It shows an unparalleled extreme sensitivity, and this can shorten the measurement time by a factor of 10. So this means if you normally measure at a certain bandwidth in 10 hours, you can finish now your test task with a ZNA in 1 hour. The internal IF of the ZNA is directly accessible for external downmixing, high measurement frequencies to reduce the losses. The highlight is here the broad IF bandwidth of 1 gigahertz, so you have a wide frequency range to select your frequencies from. If it comes to pulses, arbitrary pulse sequences can be modeled with 4 pulse generators and 4 pulse modulators. Last but not least, the enhanced trigger and sync function. This leads to more accurate measurements because the positioner and trigger can exactly be matched by functions like segmented sweep, cascaded, trigger, and so on. So all what you need to measure effectively in an anechoic chamber. The millimeter wave converters, they extend the frequency range of the vector network analyzers up to 1.1 terahertz. And so it makes them the perfect analyzers for measuring microwave antennas and other components in the millimeter wave domain. They are also featured with a user-intuitive GUI and a wizard, which guides you easily through the process. And this makes the measurement setup very easy and user-friendly. Before I dig deeper into the antenna measurements, I want to explain the different antenna field zones. So close to the antenna under test, you find the reactive near field, and mostly reactive field components are predominant. In the radiating near field, you find a mix of reactive and radiating field components. In the near field, the radiation pattern is not yet fully developed. But by near field to far field transformation algorithms, the near field can be transformed into the far field quantities. And in the far field, you have then the radiating field, which consists of locally plane waves. The size of the device under test and of the operating frequency decide about the measurement distance and if you test under near field or far field conditions. If you test in the near field, you can transform the measurement result to the far field by a near field to far field transformation, which is integrated in the AMS software. To keep the complexity of the transformation low and for precise results, it is common to measure with narrow band horns. But of course, then you often have to change the probes. Broadband probes require a correction function, but this is included in the Rohde and Schwarz software. So it is possible to measure with very wide band antennas. And the dual polarized probe antenna, it provides efficient and fast measurements in a very wide frequency range from 4 to 87 gigahertz. So this transformation algorithm, it is based on the equivalent current principle. And this gives you another advantage. The equivalent surface current densities, they can be reconstructed on a virtual surface around the antenna under test. And by means of the reconstructed equivalent current densities, what you can see here on the right-hand side, it is also possible to identify errors on the surface structure and to identify erroneous elements in the antenna arrays. So for antenna arrays with many elements, it is very difficult to detect faulty elements. And the algorithm offers an effective technique from R&D to production and validation to detect faulty elements. And the accuracy can be seen at a customer AUT, where an arbitrary element is placed in the array, so in the middle, and then on the right-hand side, you see the result. So not only errors at element level, but also in the beamforming network. So here phase shifts can appear. And all stages are marked where they can appear. So a phase drift causes a degradation in the signal-to-noise ratio, and with it, a deformation of the beam. A common LO at a higher frequency may serve to ensure phase coherency. A precise characterization of the signal path plus antenna can be performed at module level. Temperature effects, variations over time, etc., occurring in space must be pre-assessed with tests, and adequate correction values must be stored in a lookup table to compensate these effects. Also, one module can serve as calibration module in the overall configuration. So this is presented here on the right-hand side. And due to the high integration level, OTA measurements, they become essential at a very early stage in the R&D process. So considering temperature effects, the amplifiers and phase shifters required for beamforming and for beam steering are very temperature sensitive. So this means that the antenna performance and accuracy in forming the beam is influenced by the operation temperature. Temperature variations are real life in space. In order to test and calibrate the antenna array accordingly, OTA tests under different temperature conditions are required. However, performing temperature tests in an OTA chamber is difficult and for multiple reasons. So the volume of air to be heated or cooled is big, so it takes a long time to reach a stable temperature. Then the absorbers and positioning motors do not like very high or very low temperatures and might be easily damaged. But Rohde and Schwarz developed a thermal solution which avoids all these problems. It is based on a climate bubble, and you can see this here in the middle of the picture. It is placed in an anechoic chamber, and so it is climate controlled by an external thermal stream. So with regard to the entire R&D and production cycle, precise, reliable, and reproducible test results are mandatory in order to fulfill the severe test requirements in satellite communications. For every R&D stage up to high volume testing and production, the broad portfolio of OTA chambers can provide a controlled environment, reproducible test results, all-weather capability, ensure security, and minimized EM interference. And these chambers become more and more essential because antenna in a package or systems on the chip include the antenna, and so no testing can be conducted anymore after the wafer level. And this will bring in OTA at a much earlier point and will require cost-efficient OTA test solutions for production. Another principle which is realized in R&S chambers is the one of a compact test range. And it has the benefit that testing under far-field-like conditions is feasible in real time. In a compact range, spherical waves are transformed in a planar wavefront by a parabolic conditions are realizable in a short measurement distance. Here you see the wireless performance test chambers, which are available in different chamber sizes. So the convenient chamber portfolio ranges from pre-compliant to CTIA compliant chambers, and they cover the frequency range from testing. Modems and other system components must be tested as well in order that all system components are system and network compliant. And this is known and common for mobile communication systems. The test rack presented here can be scaled from subset testing to full testing in an automated and calibrated environment. In conclusion, Rohde and Schwarz provides the whole range of test devices and a capable software to realize fully integrated and customized OTA solutions. Besides OTA chambers, customized EMC chambers complete the R&S portfolio. And this means that the customer has only one single point of contact for a greater efficiency of the test solution. Thank you very much for listening.
Thank you, Yvonne. That's from different point of view for active phase array antenna. That's measurement. OK， 那刚我的同事Yvonne她